So let's talk about our scale decomposition. And the scale decomposition, the way that we're writing this specifically was that we had some Sobolev space, H10, which will actually, for the purpose of simplifying my notation, I'll write as V. And we wanted to decompose this into a finite dimensional approximation space, VH, and a direct sum with all that is remaining, the fine scale space, V prime. So right now we have a clear-cut definition for V, and we have a clear-cut definition for VH. So it might seem natural that this also immediately defines V prime, but actually it does not. And this is something that is not immediately clear, so that's why I'm addressing this in a particular video, because this has some ramifications. So this decomposition is in fact not so trivial. So let's take it back one step and start thinking about what this decomposition should mean. What this decomposition should mean is that this formulation is well posed. This should be a completely equivalent formulation to the original weak statement set in the Sobolev space H10. It should be completely equivalent. And for those two to be completely equivalent, this decomposition needs to be unique. So there needs to be a unique decomposition of U, any U, into one specific UH and one specific U prime. And again, that is not unique, and that comes down to how we define a good approximation to U in our approximation space. So we'll see that that actually has to do with precisely this, the way that we decompose the scales here. So what we require that for each and every function or entry in V, and I'll purposefully not use U here because I want to emphasize that this should not only hold for the solution to our partial differential equation, but in principle for anything that lives in V. So for each psi in V, there is a unique psi H in VH and psi prime in V prime. And you might still think, well, isn't that obvious? If you have a certain approximation space, then psi H is simply going to be, well, the solution in that one, and then psi prime is going to be, well, whatever is left. But let me show you with a pretty simple example that a decomposition like this is in fact not unique. So let's take the example where we're saying that V is simply not a function space, but rather a space of vectors. So we're going to say V is R2. Yeah, so we're completely changing from functional analysis to linear algebra right now, but I hope that in my earlier videos I emphasized enough that there was a very strong connection between the two. So this is not a function space, this is a space of vectors, but it serves to illustrate my point. So R2, well, that's the plane, right? So we have a plane. So this is R2. So that's going to be our V. And suppose that I have now a finite dimensional subset as VH. Yeah, and in our functional analysis case, where V is composed of functions, our finite dimensional space is also composed of functions. But right now, our finite dimensional space consists of vectors. And I actually define this as the span of a single vector, suppose 2, 1. So what is the vector 2, 1? Well, x goes forward 2 steps, y goes forward 1 step. So this is the vector. And the span, VH, is going to be, well, any linear combination of that vector. So that is this entire line. So this line is precisely what VH would be. It's going to be a subset of our complete V. just in the way that our finite element approximation space is a subspace of H10. So now you would say, well, naturally V prime is going to be everything on top of that, but actually not quite so simple. Let me draw this twice, and then I'll show you that there's actually not a unique decomposition. So suppose that I now take some object, or a point in this case, in our original space. So that's going to be this psi, the point right here, psi. And take the same point right here. And then we're going to define a VH and a psi H and a psi prime. Well, I could project this psi perpendicular onto VH. And say, well, that's clearly going to be my coarse scale solution. So what is then my fine scale solution? The fine scale solution is going to be, well, apparently this vector. But my fine scale solution is only this vector because I chose this way of defining my coarse scale point. And I could have instead decided not to project orthogonally, but maybe planar according to the y-axis. So I could have defined my psi h to be this point right here. And then my psi prime would be this vector. So in the first case, whenever I take any point and I project it perpendicular onto that plane, my fine scales will always be perpendicular to the line 2, 1, which makes this the fine scale space. So in this case, our fine scale space is defined as the span of -1, 2, the vector orthogonal to 2, 1. In this case, if I project any point along the y-axis, then naturally any fine scale solution is going to live in this plane. So then suddenly this plane has become the fine scale space. So we see that we have different choices of fine scale spaces, and these choices, they correspond to the way that we define a coarse scale function or a coarse scale point for any given point in the complete space. So in the second case we have V prime as the span of, well, actually just the y-axis, right? So 0, 1. So even though the original space V is fixed, and even though VH is fixed, V prime remains flexible. And it depends on the way that we define our coarse scales for any given original point. So V prime depends on our choice of map from psi to psi h. And the way that we define this a bit more technically correct is that it depends on our choice of projector. Projector P. Such that now we define psi h as the projection of any psi. So in the first case we use an orthonormal or an orthogonal projector, and in the second case we use something we call an oblique projector. And again, it's not obvious that you would want to choose the first one. This is really a choice, and this choice follows from your definition of what do I find, or how do I define a good approximation of the original function. So Let me explicitly say that. P can be orthogonal. First example. And P can be oblique. Second example. So after we've made this choice, somehow our fine scales immediately follow from that, and our fine scale space does as well. So how does that work? Well, we can actually make we can link the definition of V prime on the definition of P in the following way. First, we're going to say, well, after our choice of P, we have a well-defined and unique decomposition, psi as psi h plus psi prime as the projection of psi plus, well, whatever remains. And thus we also have an exact definition of psi prime. Psi prime as psi minus p of psi. And we often write that as, well, the identity operator on psi minus the projection operator on psi, or the operator is I minus the projector times psi. It's an equivalent way of writing. So how do we obtain the definition of the fine scale space from this? Well, we have a certain number of requirements on P that we need to impose, and that are also quite logical. First of all, we need that, so we require that the projection of any core scale solution is going to be that core scale solution. Now, in the case of a projection on a 2D plane, that is quite obvious, but not necessarily, you wouldn't have to make this choice. But naturally, if I choose an orthogonal projection or the projection that you see in the bottom, then you find that if I were now to project this point psi h, and I would project it orthogonally onto the space VH, well, naturally that would end up at the same point, right? So we have that the projection of the projection is going to be equal to the projection itself. So the way that we can also write this as P psi is going to be equal to P psi, and sometimes also just write P is equal to P. So this property is a property of any operator can have this property, and this is what we call idempotency. And secondly, we require that our projectors are linear. So that means that if I project psi plus zeta, then that's going to be the same thing as the projection of psi plus the projection of zeta. So we have those two properties. We have a property of linearity and we have the property of idempotency. And if we have these two properties, then I can actually get a very nice definition of my fine scale space. Because what we see then is if I take the projection of any fine scale function, well, then that is going to be equal to, well, the projection of psi minus p psi. Due to linearity, that's going to be the same thing as p psi minus p squared psi. Due to idempotency, that's going to be the same thing as p psi minus p psi, and that's going to be equal to 0. Now, does that make sense? Well, have a look at these pictures. You can see here that my fine scale solution, this point right here, if I were to project that onto the core scale space, well, then it would end up at 0. So indeed, that's what we see is happening. Same thing here. If I take my fine scale point and I would use this oblique projector that falls straight down, then we would obtain, again, the 0 point. So this is not only coincidentally true, this is actually how we're going to define our fine scale space. So our fine scale space V prime is defined as all the possible points or functions later on, psi in the original space, under the condition that the projection of that point is equal to 0. That is our rigorous definition of the fine-scale space. And with this definition, we have a nice direct sum in the sense that any psi is uniquely defined as some component in VH and some component in V prime. So the projection operator here does not occur explicitly in our formulations in the way that we write this, but implicitly through that definition of the fine-scale space, through the definition of our scale decomposition. So I focused on linear algebra here because that's something I can draw, but we're interested in functional analysis. So I should emphasize now that the same concept applies for function spaces. Where we're going to say H10 is defined as a direct sum between VH plus V prime, and then given any function u in H10, we have to define some operation to determine what we find to be a good approximation to that u. So what we have to determine a suitable UH in VH. So a suitable approximation. So for any possible solution or any possible function in H10, we have to define, we have the ability to choose an optimal solution in our finite dimensional approximation space, in our finite element space. And precisely this operation from taking a function in H10 and choosing a function in UH, we can write that as this operator P acting on U. And then we still have the same conditions where the operator, which you can think of as a choice, where our choice has to satisfy that it is linear, so that the P of some solution U1 plus a solution U2 is going to be equal to the projection of U1 plus the projection of U2, and it has to be idempotent. And that meant that the projection of U is going to be equal to the projection of U. Right? Those were the two demands that we also had in our linear algebra equivalence. And given those two demands, the projection, our choice of a good solution, implies a scale decomposition, implies a fine scale space. And under these two conditions, this operator is also immediately called a projector. Now, so we think of projectors as typical linear algebra things, where we take vectors and project them onto planes. But as with pretty much everything from linear algebra, it extends to functional analysis. And in this case, any operator, any mapping from some space onto a subspace that is both linear and idempotent is by definition a projector. And then we immediately have that, so an immediate result is that the fine scale space V prime is equal to, well, all the functions u in H10 such that the projection of u is going to be equal to the zero function, the function that is zero everywhere. Yeah, so that's a direct extension of what we saw in linear algebra. And this is actually something that we give a name. This is called the kernel of the projector, or the null space of the projector. So all the functions whose projection yields the zero function, all the vectors whose projection yields the 0 point, the zero vector, that is what we define to be either the null space or the kernel of that projection. So with this knowledge, our VMS decomposition, our VMS formulation becomes that we search, we find a solution UH in our finite element approximation space and a fine scale function that lives in the kernel of the projector, such that for all VH in VH and V prime again in the kernel of the projector, we have, well, those two lines that we saw before, BUH, VH plus BU prime, VH is equal to LVH, and BUH, V prime plus BU prime, V prime is equal to LV prime. Okay, and pretty much that's everything I wanted to talk about when it comes to the skill decomposition. But I hope that you appreciate that there's actually quite some significant results coming from this. The results that we can already immediately see is, well, first of all, we have a choice. We have a choice of projector, and that means that we get to choose, as numerical analysts, we get to choose in this framework what we find to be a suitable approximation UH in our approximation space for any given function. We get to pick a suitable operation that gives us a nice approximation for any possible function. Now we have to have a mathematical definition for that, naturally, to be able to use that, and we have some mild constraints, linearity and idempotency. So that's the first thing. We have a choice. Secondly, that choice does not directly affect our finite element spaces and our finite element functions. Not directly at least, only implicitly via these fine scales. So then how is that going to affect our finite element formulation? Well, again, via the model that we have to substitute here in place of the fine scales. And we can even go as far as to say that if we substitute the correct U prime in here, then you would exactly get the UH, the finite element approximation, that you have defined to be the perfect approximation to the original function U. Now, in general, we cannot do that because these U primes become too complex, and also this BU prime, VH becomes too complex, but we can get very good approximations of that. And in certain simplified cases, and I'm thinking of one dimension here, in one-dimensional cases for advection diffusion equations, we can actually invert these relations exactly. We can exactly choose the kernel of this projector. We can define that space very nicely, and you can get the exact optimal solution. So I would say that's the third thing we can take away from this. Yeah, so it might seem like a bit of a technicality, right? The skill decomposition, but it has very profound results in the whole setup, and results that are not immediately clear, but become clear as you're working with the fine scale modeling. And that's also something that we have to take into account during the fine scale modeling. Now, this naturally opens up a very big question that we have to answer next, and that is, what choice of projector might we make? Is there certain obvious choices? Is there certain obvious choices of what we do not want to have? And in general, what would a projector look like, given that we're dealing with function spaces rather than linear algebra? Yeah, so that's going to be the next video, our choice of projector.